Section 4.1, the definition of the Laplace transform. Welcome to Chapter 4, in which we'll be investigating Laplace transforms, more specifically how Laplace transforms can be used to solve certain types of differential equations. In this section, we'll only work through a small number of examples. I will primarily be introducing the idea of a Laplace transform and, quote, transforms more generally. In this first portion of the notes, I've tried to explain the perspective I'm used to taking on the Laplace transform. I ask that you read through this introductory portion carefully on your own. I'll only briefly be discussing some of the ideas here. So what do we mean when we talk about a, quote, transform? In a rough sense, I think of a transform as a function whose input is a function. Typically, we think of the input of a function as a number. Here, the input is not just a number, but a function, something like sine or cosine or natural log. From this perspective, there are other operations we're familiar with that could be considered, quote, transforms. I've given two examples here. The differential operator, dx, and a definite integral, say from 0 to 1 of some function of x. If you think about it, both operations act on a function. So you could think of that as the input, in which case these operations would be functions whose inputs are functions. What's interesting about these two examples is that the first example, the differential operator, dx, transforms one function to another function. Both the input and the output are the same type of mathematical entity. They're both functions. With the definite integral, the input is a function, but the output is something different. It's a real number. So this operator transforms a function into a different type of mathematical entity. It transforms from a function to a real number. So how about the Laplace transform? As the name suggests, the Laplace transform is something that takes functions as inputs. More specifically, we usually think of our input functions as being functions of t. And we typically think of that t variable as representing time. As you'll see in a second, the definition of the Laplace transform contains a variable or parameter s. Once we have completely evaluated the Laplace transform of an input function, some expression of s will be our final product. Some expression of s will be our output. So we often describe the action of the Laplace transform as taking in a function of t and outputting a corresponding function of s. So this operator will take in a function of t and spit out or output a function of s. In fact, in most contexts in which Laplace transforms are used, the t variable does represent time. And in a way, the s variable indicates properties of oscillation, period, frequency, wavelength. So you'll commonly hear it said that the Laplace transform moves from a function of time, moves from the time domain to the frequency domain. So this output, which is a function of s, is often described as being in the quote-unquote frequency domain, because this variable s can, in a way, indicate properties of oscillation. In order to see that relationship, we would have to go into more detail than we'll be able to provide in this class. So we won't have a chance to discuss that full connection between time and so-called frequency. But if you'd like to know more about that, send me an email or visit office hours. I'd love to talk about it more. So what's the point? Why do we want to transform from t as an independent variable to s? Well, as you'll see in the next section, if we can transform an entire differential equation, the result will be an algebraic equation. So we'll start with a differential equation, something that contains unknown derivatives, and the result after we have applied the Laplace transform will be an algebraic equation, an equation which does not contain derivatives. In general, algebraic equations are easier to solve than differential equations, so that's a plus. Two other things I mentioned here. First, there are certain types of functions that are sort of bothersome in the context of a differential equation, and we can incorporate those types of functions more easily if we use Laplace transforms as our tool for solving that differential equation. And the last benefit I mentioned here really requires more exposure to Laplace transforms than we'll be able to get in this course. But it is true that if you work with them extensively, you can start to identify properties of the solutions of the differential equation without fully solving that differential equation. This kind of relates to the, quote, frequency domain perspective that I mentioned earlier. Anyway, all of that is my brief attempt to provide some context for Laplace transforms. The main takeaway is that we will put a function of t into the Laplace transform, and we will get out a function of s. And this process will enable us to solve certain differential equations more efficiently. With all that said, let's finally take a look at the definition of a Laplace transform. Definition 1. My input function f of t must be a piecewise continuous function. That just means that it can be discontinuous, but the components need to be continuous. And then if we choose to, we can sort of concatenate those components as a piecewise function. And that function has to have that property on the positive reals. So again, we're thinking of t as representing time. So we pretty much exclusively will neglect or exclude negative t values because negative time values don't typically make sense. So then the Laplace transform of such a function, which is denoted this way, where I've said the L operator is applied to f of t, or we'll denote it by capitalizing the letter which represents the name of the function. It's given by this formula here. So I'm going to take my f of t, I'm going to input it into this integral, and then evaluate. At the top of the next page, I sort of read through this definition to try to understand what we're going to do to our input function. So let's look at what we've got. First, I'm going to take my input function, I'm going to multiply by e to the negative st. E to the negative st, if s is positive, will be a vanishing exponential. That is, it'll be an exponential that is approaching 0. So when I multiply that function by my input, the overall integrand is getting pushed toward 0 because this exponential will be pushing the overall integrand toward 0. And then I'm going to try to evaluate this integral from 0 to t values that grow without bound. If you remember from calculus, this type of improper integral doesn't always converge. And so you'll notice in the definition, I'm going to force this integral to converge. So I will only consider values of s which lead to a convergent integral. So the way I think of the Laplace transform is basically I want to try to identify which values of s will force this overall integral to converge. Let's take a look at a couple of examples. In each of the examples that we have presented in this lecture, after we've evaluated one or two examples, we're going to try to generalize from those examples to identify a general rule about the specific family of functions that we just investigated. So here in example 1, I've picked pretty much the simplest function I can think of, f of t equals 1. So if I want to take the Laplace transform of f of t, I could also write that by inputting the specific function inside my braces. And according to the definition, that'll be the integral from 0 to infinity of my input function, which in this case is just the number 1, times e to the negative st dt. Now remember, s here is a parameter or a constant or a variable, and this integral here is an integral with respect to t. So I'm imagining integrating something like e to the negative 2t or e to the negative 5t. I'm going to treat this s the same way I would treat another constant. This integrand obviously just simplifies to e to the negative st. So evaluating that integral, I get e to the negative st back, and then I'll have to divide by this coefficient as sort of an application of u substitution. And I can't forget that I'm going to evaluate this from 0 to t values that grow without bound. To accommodate this infinite limit, I would like to explicitly write a limit. So this value, will be the value of my expression when I have plugged in this bound. I'm putting plugged in quotes because I can't actually plug in the number infinity because infinity is not a number. So I'm accommodating that using this limit. And then I will plug in t equals 0. And now, so long as s is positive, this exponential will decrease and will approach 0 as t grows without bound. That requirement that s be positive is essential, so I have to make note of that. Notice also that I can't include s equal to 0 because I have these s's in the denominator. So s has to be strictly positive. So if s is positive, then this first term, this limit term, will go to 0. So I'll be left with just this second term. E to the 0 is obviously 1. So my final answer here will be 1 over s. So that's our first Laplace transform. The Laplace transform of the number 1 gives me the function 1 over s. And that is only true if I look at positive s values. This restriction on s is very common, and it makes sense because we're restricting our t values to be positive, so it sort of feels natural to me that we would also restrict our s values to be positive. What I'd like to do next in Theorem 1 is generalize that result. I had the number 1 specifically here as my input, but if it had been any other constant, I actually could move that constant outside the integral. Or I could think of that constant as just remaining in this numerator throughout this calculation. So I think if I was to find the Laplace transform of any constant, the result would simply be k over s. One more quick note about notation. As I'd mentioned previously, if my input function is lowercase f of t, we often write our final output, our Laplace transform, as capital F of s. As you'll see later, it's important for us to distinguish between the original function and the transform. And so this method of using the lowercase letter for the original function and the corresponding capital letter for the transform is pretty common. All right, let's try another one. In example 2, we're asked to compute the Laplace transform of e to the 2t. And you'll notice that again, I've left myself room to generalize this specific result. So as I do these calculations, I'm going to keep track of this 2 and think of how the transform would change if there was another constant in that exponent. I will, of course, start with the definition, and here I've plugged e to the 2t into that definition of the Laplace transform. In my integrand, I have two terms that are exponentials with the same base. Since they're multiplied, I can combine them into a single term by adding their exponents. And then here I've gone a step further and actually factored the t out in the exponent. Now remember, 2 is a constant and s is also being treated as a constant. So this integral has basically the structure of e to some constant times t. So when I write an antiderivative of that, I will once again have this exponential term, and then I divide by this coefficient. This is sort of a lazy way of enacting u substitution. Now, in order to deal with my bounds, I will once again introduce a limit as t grows without bound of this expression, and that accommodates this upper bound in quotes. And then I will plug in t equals 0. And once again, I want to force this integral to converge. Therefore, I want to make sure that this component, this coefficient here, is negative, which will lead this overall exponential term to go to 0. So since I want this term to go to 0, I need 2 minus s to be negative. I guess that's equivalent to saying s is greater than 2. And when I have this restriction in place, this term will go to 0, and so I'll just be left with this fraction here. Once again, e to the 0 is obviously 1. I'm actually going to push this negative down into that denominator. So I'm going to write my final answer as 1 over s minus 2. So if we look back over this computation and try to figure out what role 2 played, it's clear that I could modify this by using any other constant, and then that constant would be factored out, and so then my denominator here, instead of being 1 over s minus 2, would be 1 over s minus whatever that other constant was. And then this Laplace transform would be defined for s greater than that constant. So take a second to just verify for yourself that if I was to change this to say a 9 or a 26 and then redo all of these same calculations, I would simply get 1 over s minus whatever that coefficient in the exponent was. So I'm going to write that here in theorem 2. It says for any constant a, the Laplace transform of e to the at will simply be 1 over s minus a. And that's our final example for this section. As I mentioned, I wanted to just use this section to introduce the idea of a Laplace transform and provide a few examples, 2 in this case, which demonstrate how we calculate it and some of the basic properties, and kind of just to start to get a feel for what the Laplace transform is. In the next section, we'll work through quite a few examples to start building up a library of transforms of known functions.